Thus far, we have spoken about first principles, so finding the derivative using first principles, and then we've started chatting about the shortcut rules for differentiation. So remember, you will only ever use first principles if the question says to. So if it says determine the derivative using first principles, then yeah, unfortunately, got to substitute an x plus h into f of x, do all of those fun things and find your derivative. If they don't, you'd use the shortcuts, right? So remember I said to you that there'll be the first two questions in calculus will be a first principles question, and then the next question will be what we've been doing Wednesday and today in terms of slightly more complex expressions. And we're going to test whether or not you know your notation, whether you know your rules, know how to get your expression in the correct format, etc., etc. Once we move on from this, the expressions that you're asked to derive are really not that complicated. So it'll be cubics, it'll be quadratics, nothing really more than that. So differentiation really does become very easy after these questions. But we need to be able to do them because it's pretty much the first 10 marks of calculus. So 10 of those 35 marks is just first principles, understanding notation, formatting, etc., etc. So what we have learned so far, and like I said, I will go through this example one in a second. And obviously I didn't leave myself any space because that's a choice I made. What we know so far is that I can't draw a star. So we'll try that again, is that format is very important. So when I say format, I mean the way we write our terms in our expression. It needs to be the sign, then the coefficient, the number, then the variable, and then that variable's exponent. Doesn't matter if it's negative, doesn't matter if it's rational, that is how we want it. We never want an exponent in the denominator, we never want surds. And the second thing that we've learned is that if you are given an expression, for example, x to the power n, to find the derivative, what you will do is you will take that exponent, times it by your coefficient, and then subtract 1 from it. Those are the two sort of really important takeaways from last week, Wednesday's lesson. What we're going to chat about today is slightly more complex expressions and dealing with what's going on here. So dealing with the fact that we never want brackets, i.e. we always want to be working with a simplified expression. We never want divide lines, fractions, which we've kind of already spoken about, particularly when it comes to variables. We never want a fraction. And obviously we already know we don't want root signs. So these are the things that we're now going to focus on. The expressions are going to be a little more complex, but it's nothing we can't handle. Cool. So I had asked you to try example 1 for me, which I'm just going to move over here so that I've got some space. If you've tried it, awesome. If you haven't and you've just joined, that's also cool. Don't stress about it. But let's have a look at example 1, just to ease us back into this whole using our rules, and then we will move on from there. Okay, this seems very big, but we're just gonna roll with it. Okay. Now this first one, I have no issues with my format. It's exactly as I wanted. Sign, coefficient, variable, exponent, no problems. I can go straight into my derivative. This is where I'm going to have to use my rules. Let's try that again. And my rules say as follows to me. I need to take my exponent. So in this case of term 1, it's 4. I need to multiply that by my coefficient. 4 times 1. I don't know what's happening. I'm just going to leave it. And so my derivative is 4x. Subtract 1 from that exponent to the power of 3. That doesn't look like a 3. So let's deal with that. To the power 3. Move on to our next term. An exponent of 1 for that x. 1 times 6 is 6. But now when you subtract 1 from that exponent, it becomes to the power 0, which is 1. 6 times 1 is still 6. Anytime you have a constant, that derives to 0, right? English. It falls away. And so your derivative, once you have done all of that, is 4x cubed plus 6. That's it. That's applying the rules that we've already learned. Nothing further is required of us. So let's now have a look at something a little more complex and actually now dealing with some of the things we spoke about earlier. This does seem excessively big, but we're just going to roll with it. So what I said earlier is that we always want to simplify. If we have a look at this expression for g of x, this is not simplified. It is a bracket squared, and so I need to go ahead and simplify. Now, grade 12s, just remember you may not use the derivative notation in any form until you actually start doing the derivative. So I'm still going to use g of x because I'm not actually working with the derivative yet. I first need to go and expand or distribute my two binomial brackets before I can get to the derivative. So when I expand this, I get 16x squared minus 12x plus 9. Those middle terms simplify, so 16x squared minus 24x plus 9. That is still my expression for g of x, still g of x. However, now that it is in the format that I want it to be in, I can now go and find the derivative. So now I can introduce my derivative notation, g dash x. 16 times 2 is 32. 2 minus 1 is then just x. That x is a power of 1, so 1 times negative 24 is negative 24. When I subtract 1, it becomes x to the power 0, which is 1, so just negative 24. And that plus 9 is a constant, so it derives to 0. It falls away. We found the derivative. So you might have to do some simplification before you actually get into anything. All right, I'm just going to take a little tangent. Tangents, derivatives. Hopefully that'll be funny later on in life. Right, tangent that I'm going to take is just to remind you of the derivative notations. The most common one that we use is if you're given f of x equals, and I don't put equals, our derivative is then f dash x. We know this one, this is the one we use a lot of. The other one that we can give you is y is equals some expression. The derivative is then the derivative of y in terms of x. And the last one that we can give you is the d of x expression with the square brackets. When you found the derivative, it's literally just equals whatever it is. You drop the brackets, you drop the d of x, it's gone. You no longer need it. All right. But that's sort of, let's call it the first example, because really example 1 was just a recap, is starting to illustrate to you how important it is to have your expression simplified, to have your format correct before you go and do anything. So let's take a screenshot of those two, and then you're going to try by yourselves. Sorry, everyone. Okay. And remember, grade 12s, if you've got a question, please just put it in the chat, unmute yourself, raise your hand, whatever you want to do. Just make sure you do ask. Okay, let's sort out issues now before we get into things like cubics and functions and all of the things that is actually brand new rather than stuff that we do actually know how to do. All right, so I want you to try this one. My sad little block there hiding the answer almost is a bit pointless. But let's try this one. I've just explained how to work with this notation, but remember you only drop this d of x in the square brackets notation once you have simplified and essentially found your derivative. Found your derivative. All right, but let's try this one and then we'll have a look. I'll give you a minute or so and then we can have a see. If you've got questions, just ask. You can put your answers in the chat. Let's me check. It allows your peers to have a look at what's happening. But let's try. Right, sweet children, let's have a look. I don't think too tricky. Obviously, the first thing that we need to do is we need to distribute. So we need to simplify that whole situation. Once that's done, you find the derivative. Nice and easy. Okay. Hopefully nothing too complex yet. But again, just shout if you need help. Take a screenshot of this if you want. Otherwise, let's have a look at our next example. Okay. So example 3, here over. We once again have the same d of x squared bracket notation, but now not only do I have a bracket that I need to distribute, I also have a square root. So remember, we never want surds, so we never want roots, and we always want to simplify. Now guys, I don't know if this is the nice thing about exponents or the ugly thing about exponents, but often there's so many ways to do the same thing. So in this case, if you want to square those brackets first and deal with the surd later, do that. If you want to deal with the surd first and then square the brackets, do that. If you want to deal with the surd sort of halfway in between your simplification, do that. It honestly makes no difference. So you decide at the end of the day. Some people like to just deal with the surd, get it over and done with, and then move on. Some people would prefer to distribute and then deal with the surd. It doesn't matter. This time I'm going to deal with the surd first, because why not? But you do what makes sense for you. All right. So we're still going to keep the notation because obviously I'm not yet finding the derivative. When I do find the derivative, I will drop the dx and square brackets. Okay, so in my bracket, x squared minus x to the power a half. Remember that the square root of x is x to the power half. I actually don't like what I've done there. Let's actually just square this bracket. And so I'm multiplying this bracket twice. Right, this is now where your exponent law knowledge becomes important. So when we start to distribute, x squared times x squared, relatively nice and easy. We have got x to the power 4. But now I've got x squared times x to the, or negative x to the power half. Now when we multiply with exponents, we add them. So x squared times negative x to the power half, firstly a positive times a negative is a negative. And then when you add 2.5, you get 5 over 2. So minus 5 over 2. Negative x to the power half times positive x squared gives us another x to the power 5 over 2. And then negative x times a half, no, let's try that again. Negative x to the power of a half times negative x to the power of a half. Negative times negative is a positive. A half plus a half is an exponent of 1. So I've simplified this whole situation. Right, if you didn't and you dealt with surds later, that's cool. This probably makes a bit more sense. Actually, I did the other way first, but this probably makes more sense. You've got like terms in the middle there, so let's just neaten that up. X to the power 4 minus 2x to the power 5 over 2, because there's 2 negative x to the power 5s. Sure, there's 2 of them, plus x. Now we can start with our derivative. My format's correct. I've got what I want, but now I can start with my derivative. So now I drop the dx and the square brackets. Derivative 4x cubed minus, now 2 times 2.5 is 5, so minus 5x, and we need to subtract 1 from that exponent. 5 over 2 minus 1 is then 3 over 2 plus 1, because that x derives to just a positive 1. This example here is very much like what you can expect in an exam or an assessment type scenario. It's testing your formatting in 2 ways. So it's testing dealing with the surd, it's testing the simplification. It's then obviously bringing in some lovely rational exponents and testing quite at quite a high level the application of your rules, subtracting 1, multiplying your coefficients and so on. And then it's obviously testing your notation. So this is a very good example of what you can expect in the questions after your first principle question, where we're testing those sorts of things. Right, this was quite a complex one, so I'm just going to wait here for you to take screenshots, but also in case anyone has a question they want to ask before I move on to the 4th example. Yes. Right. Oh, gosh. Okay, so example 4 is now an example that deals with the issue of a fraction. I don't want fractions. Simple as that. In Wednesday's lesson, we have already dealt with fractions, but we dealt with fractions where like the x was in the denominator or you had a third in the denominator. We haven't dealt yet with ones where we've got a binomial expression in our denominator. Now, this should take you back to your algebra from grade 10, grade 11, where we learned that we can, in order to simplify an expression, we can use factorization. So when it comes to fractions, there's going to be two scenarios that you get. Scenario number 1 will be like this one and the next few examples, where we need to use factorization in order to simplify. Scenario number 2 will be where our denominator is not a binomial, it's a single term, but our numerator is maybe a quadratic or a binomial or whatever. And in that case, because you can't factorize anything, you would have to separate your fraction. So you'd have to take that denominator and split it to your numerators, thereby separating or I had a word earlier and now it's gone. Separating your fraction. So there's two ways we can deal with fractions. Usually it's factorization, but it's not always factorization. So we will do an example a little later, splitting our fraction. If we have a look at this though, we need to factorize. Now guys, as you do more of these, you'll see that there's like a little hint given to you. Remember, your goal is to get rid of this denominator. The whole point of you going ahead and factorizing, I don't know what's happening, is to get rid of the denominator. So some way you need to realize that when you factorize this numerator, one of those factor brackets must be 3x minus 2. All right, I'm going to show you how I factorize quadratics. There are many ways that you can factorize a quadratic. I don't care. Right, I'm going to show you mine and then I'll tell you some of the other ways that you can do it. Do what works for you. So the way I do this is I go to my first term, so 3x squared, and I know to get 3x squared, I would have to say 3x times x. I then go to my last term, 2. I'm going to ignore the signs for now. And the only way for me to get 2, or the factors of 2, is 2 and 1. I need to decide where I should put it. But again, I'm going to use my little noggin. I know that I need a bracket that looks like 3x minus 2. So I'm going to put the 2 in line with the 3x because what's eventually going to happen is these are going to become my brackets. So there's my 2 times 1. Cross multiply. So x times 2 is 2x. 3x times 1 is 3x. And then I go back to my expression. My middle term needs to be a positive x. So I need to now ask myself, what do I do with 2x and 3x to get a positive x? Well, I would say 3x minus 2x. That gives me my middle term of positive x. That means the 3x, this answer, its line must have a positive sign, and the 2x line must have a negative sign because it needs to be a negative 2x. They are my brackets. Now, that does make sense to you. If you have a better way of doing it, if you have a way of doing it that makes more sense to you, that is what you do. You do not listen necessarily to what I've done if it doesn't work for you. So f of x, when I factorize, 3x minus 2, x, what was it, plus 1. And then in my denominator, that 3x minus 2. Those simplify. So we cancel that. And we have f of x is equal to x plus 1. Right, I will carry on in a second. Some other ways you can factorize. Some people, I'm not going to say cheat, but cheat and use their calculator, especially if they've got a silver or a white calculator. Those actually factorize for you. Alternatively, just use a quadratic formula. It's there for a reason. It works for any trinomial. Why not use it? Okay, you don't even have to do much. You literally just show your substitution and then your two answers. Use the formula if you're not sure. All right, so we now can find our derivative. Use your notation. This exponent of x is 1, so 1 times 1 is 1. X to the power of 0, 0. So x, no, I don't know what I'm trying to say there. X to the power of 0 equals 1. So 1 times 1. That's it. This is a constant, so derives to 0 anyways. So actually my derivative here is actually just 1. Now, there is nothing wrong with you getting a constant term as your derivative, right? It's not wrong. It's not an issue. As we do more graph work, it'll become easier to understand what that means. But because we are somewhat flying and because I think it's really interesting, I'm going to explain to you why we get a derivative of 1 in this case. All right. So, sorry, I'm going to need my charger in a second. My first question to you guys is, what type of graph? So what type of graph does f of x equals x plus 1 represent? You can put it in the chat, you can shout it out, whatever. What type of graph is that? Nice. Okay. So it is a linear graph. Now remember, straight line graphs have a general formula of y equals mx plus c. M is your gradient, c your y-intercept. If we were to plot that graph, now I'm going to plot it very roughly. It's not going to be perfect, but if we were to plot that graph, it would look something like that with that y-intercept at 1. It's a positive graph, all of those beautiful things. What is the gradient of this graph? So of this linear graph, what is its gradient? Nice. Okay, the gradient is 1. So coefficient of x, 1. Boy. Okay. Now, if you remember from our, that's trying to be a 1 in front of the x. I'm just going to accept it. If you remember from our very first lesson when I was explaining what is the derivative, why do we use differentiation, what does it do for us? One of the things that it allows us to do is it allows us to find the expression of a gradient. That wasn't very well put. Let me try that again. It allows us to find an expression that describes the gradient along any graph. We usually work with curved graphs. So we usually work with quadratic or parabolas and cubic graphs. And we're going to focus a lot on cubic graphs over the next few lessons. However, this is a linear graph. The derivative tells me about the gradient. And because this is a straight line graph, the gradient is constant anywhere along that graph. And so that's why our derivative is just 1. If we had a parabola, for example, so let's say I had my parabola, I don't know, 2x squared plus 3. The derivative of that would be 4x. There is a variable attached to it. Because along this curve, my gradient changes. It's negative, 0 at the turning point, positive. If you were to think of a cubic function, I'm running out of space here, which we will get to this year. That's a cubic. I know, x cubed plus 2x, whatever. The derivative would be 3x squared plus 2. And we'll chat more about why it's a parabola later. But again, the gradient along this function changes as you move along. So we have to have an x there to account for all the different gradients as we move along. But a straight line is a straight line. The gradient is, that's it. It's constant throughout. And so that's why when you end up with a linear expression that you then need to find the derivative of, causing my own chaos here. When you end up with a linear expression that you then need to find the derivative of, you will get a constant value because a linear graph has a constant gradient. I think that's quite interesting. You don't necessarily need to think the same thing, obviously. I just like maths. But we're going to talk a lot more about gradients, use of the derivative, etc., etc. Right, so take a screenshot. You can see the you try question. So I'm not going to scroll too far, just in case you want to keep things there. So give this one a try, and then we'll have a look. I'll give you 2 minutes, and then we'll have a look. I just need to plug this in. I'm not going anywhere, but give it a go. Right, guys, let's have a look. Ongunkosi, very nice answer. I do tend to agree. Let's see. So first things first is you need to sort out the fraction there. This one's a little different to what we had in this previous example 4, in that the denominator is a single term, but you've got a common factor in your numerator of t. So when you take out that common factor of t, it means that it simplifies because t divided by t is 1, and so you've got a quadratic. From there, you find your derivative, 2t minus, I don't know why I said minus 1, guys. No, I do know why I said minus 1, because it's minus 1. From your first term, 2 times 1 is 2, t, and then here, just be careful, it's minus t to the power 1. So 1 times negative 1, negative 1, subtract that is just 1, so minus 1. Alrighty, I don't know how many of you did take a screenshot, so I'm just going to make it smaller so you could screenshot both of these, and then we'll have a look at the next example. There we go. Oh, Bongi and Corsi, me too. Don't even stress. Like, me and signs are quite something. I also like to sometimes leave off a variable. It comes with practice, and I mean, I've been doing this for years now. I still make stupid mistakes. So that it comes back down to check things, but don't even stress. It happens to the best of us. All right, let's have a look at example 5 here. I also completely believed your +1 because I doubted my own ability there for a second. So don't you stress. Oh my gosh. Anywho, all right, let's look at this one. So we want the derivative of this expression that is in terms of p, and we've got 2p squared plus 3p plus 1 divided by p plus 1. So I'm actually going to ask you guys to try this one, even though it isn't a you try one. I want you to try it because it's more reminiscent of example 4 that we spoke about. So you're going to need to factorize and then find your derivative. So I'll give you another 2 minutes and then we'll have a look. All right, let's have a look. Okay, so We obviously need to factorize first. We can't do much until we've simplified the fraction. So keep all your notation. You're not finding the derivative yet, but this will factorize. And again, use your denominator as a hint. That's one of the brackets. Okay, it has to be in order to cancel out. So based on that, my other bracket must be 2p plus 1 all over that p plus 1. And so simplify. So the expression I'm working with the derivative of is 2p plus 1. Now that you are finding the derivative, you drop the square brackets in the dp, and you just have equals 2. That's it. And this goes back to the discussion we just had. This is a linear function. According to its equation, its gradient is 2. And so because the derivative represents the gradient, it's equal to 2. So as you start to sort of understand what the derivative is more and more, and you start to link it with functions, because it does have a very strong link with functions, as you're going to see as we move on, it does sort of allow for just like these little mental checks. I know I'm on the right track because of what I've been given here, that linear function's gradient. I know that that answer is correct. So like I said, as you just get more comfortable with these things, little checks become apparent. All right, but let's have a look at example 6. I'm just going to move that bad boy up. And this example is still one of factorization, but it's not a particularly nice one because if you look in your denominator, immediately that should be alarm belling from like grade 10, grade 11, where we would always make you switch the terms. Okay, so if you don't know what I'm talking about, remember, if you have an expression, of let's say 3 minus x, but you want that expression to become x minus 3. The way to do that is to take that expression and multiply it by -1. That will give you x minus 3. And so we're going to want to do that to our denominator, times it by -1. Now, you might say, well, how do I know that? Because you're going to have to. If you think about what you're going to factorize in your numerator here, you're going to take out an x as a common factor, but then you're going to have a trinomial. That trinomial will have an x first in its first term's position. So we want the x in the first position. Now, when you choose to make the switch is up to you. I generally like to do it first because then it's out of the way. But also just bear in mind that the goal of you going ahead and then factorizing is to get rid of your fraction. So what I like to do is I like to bring the negative up to my numerator. It's not going to change anything in my numerator, but I like to write it there in my numerator just so that when I do eventually simplify, I'm not stressing about it. You don't have to do that though. All right. However, we are going to first simplify this expression. First things first is I can take a negative out in my numerator. And so that would leave me with 3x squared minus 7x minus 6 all over the minus x minus 3. Okay, we multiplied it by a negative. It swapped. Oh, gracious. Okay, so now that we've got that, we know that we're going to have to factorize that trinomial and eventually get rid of my denominator. So this is what I'm saying. I like to then just bring this negative sign up into my numerator and write it as minus x. It doesn't change anything. Nothing's happened, right? I'm just already accommodating for the fact that I am going to get rid of this denominator. So this is over x minus 3. And now I factorize this trinomial. How you choose to do this is up to you. Obviously, remember that the giveaway is that one of those brackets should be x minus 3. Use your quadratic formula, use crisscross, use whatever method works for you. But this is then going to be 3x plus 2, if I'm not mistaken. And I am not very worried that me and my signs are not having a good day. So let me just double check myself. 3x plus 2. I am indeed correct. Okay. Those x minus 3s divide away. And so now we have y is equal to minus x times 3x plus 2. Now remember, the factorization was great. It allowed me to get rid of the fraction. But this is not a simplified expression. I still need to simplify. So I still am not at the derivative, but I now have minus 3x squared minus 2x. Simplified, no fractions, format is correct. Now I can get into my derivative. So now I introduce my derivative notation. minus 6x minus 2. Now, when we did, I can't remember if it was first principles or our first lesson on the rules, I spoke about the fact that your degree should always decrease. So degree of an expression is the highest order of the exponent. So if we go back to the original question, the degree of my expression, so the biggest exponent that I had was a cube, was 3. Your derivative should decrease by 1 degree. I don't know why I said cubed, because I'm not even looking at the right expression. So let's try that again. When we go to the simplified expression, my degree was 2. The degree of the derivative should be 1 less, which it is. This exponent of that x is 1. That's 1 degree lower. If we go and have a look here, for example, at this one, my degree of this expression was p to the power 1, which means 1 degree lower would be to the power of 0, which means it's actually just a constant. If I go to this example over here, the degree of my original expression was 2, so the derivative should be 1 lower, which it is, t to the power 1. So you should always end up 1 degree less than where you started. Right, but this one, kind of a nasty one, just because of the whole switcheroo thing we needed to do in the denominator, and the fact that in your numerator you had to take out a highest common factor and do the quadratic. But again, this is what you can expect. Okay, you can expect to be tested on your formatting and your notation when you are given questions like this. Okay, but let's take a screenshot of this one and then have a look at the next one. So the next one we're going to have a look at is now how you deal with a fraction where you can't factorize, or where factorization is actually going to get you nowhere, and how we then deal with that. And then there is one you're going to try, but I want to change it because, why not? Okay. Right, so let's have a look at this example 7. So if we have a look at what we've been given here, yes, you can factorize that numerator. You can factorize it beautifully. X minus 3, x plus 2, wonderful. But that doesn't help me. It helps me in no way to get rid of that fraction. And so what we need to do here is, this is now where we need to split our fraction. So still not derivative, but I'm now going to write each of these terms of my numerator over 2x squared. So it'll be x squared over 2x squared minus x over 2x squared minus 6 over 2x squared. So factorizing is going to do absolutely nothing to cancel out your denominators, especially when there's one term in your denominator. You need to split your fraction. All right, so now that we've split our fraction, we now go and get it into the format that we want. So we simplify. The x squared and the x squared cancel, so this just leaves me with a half. X divided by x squared would be negative 1 over 2x. And then 6 divided by 2 is 3 over x squared. Still not the format I want because I've got variables in my denominator. So I rewrite this as a half minus a half x to the negative 1 minus 3. I don't know why I put my 3 so high, so let's try that again. Minus 3x to the negative 2. Now my format is correct. From here, I can find the derivative. So now I can introduce my notation. This is a constant, so it just derives to 0, so leave it. Negative a half times negative 1 is positive a half, but now we subtract 1 from that exponent, so x to the negative 2. Negative 3 times negative 2 is positive 6. Subtract 1 from that exponent, x to the power negative 3. Now, guys, I've said this before, but I'm going to say it again. We can leave it with negative exponents. Okay, in calculus, we're not concerned about the negative exponents. If you want to write this all with positive exponents, you are welcome to, but you're not going to get extra marks for doing it. Same as you're not going to lose marks for leaving it with negative exponents. So if you do want to write it with positive exponents, this would be 1 over 2x squared plus 6 over x cubed. Again, you don't have to, so don't do it. If you want to, obviously go for it. It's absolutely fine, but you don't have to. There's no reason for you to do it. All right, so if you can't factorize and you are able to separate your fraction, that is how you will now go and simplify. What it does mean is that you will need to make sure that your formatting is correct before finding the derivative. Okay, so I'm going to leave that one up there. I am also changing this question. So give me two shakes of a lamb's tail. I'm getting rid of this -2, which obviously then means this answer is not correct because not. Right, but I'm going to leave example 7 up there. Try this question at the bottom. So x squared minus 3x plus 2 over x. I'll give you 2 minutes and then we will go through it. All right, guys, let's have a look. So again, I don't have the answer, so we're just going to have to do it together, but that's fine. So we can't factorize. I mean, you can factorize that trinomial, but it's not going to get you anywhere. We need to separate out our fraction. So it's still not the derivative. X squared over x minus 3x over x plus 2 over x. Sort out your format. So this would just be x minus 3 plus 2x to the -1. And now you can find your derivative. So now introduce your notation. X derives to 1. The -3 falls away. And so when we now say -1 times 2, it'd be -2. And then we subtract another 1 from that exponent. Again, I would just leave it there. You're welcome to write it with positive exponents if you want. So 1 minus 2 over x squared. But again, there's no reason for you to do that. We will mark you correct where am I going with the statement? We will mark you correct with the negative exponents. I see Bongi and Corsi wrote it in a different order. So minus 2x to the negative 2 plus 1, that's fine. As long as the sign is correct for the term, I don't care if the order is different. Okay, so same thing. If you had written this as negative 2 over x squared plus 1, it's fine. Again, I would not change my exponent just because there's no reason to. But you are welcome to. There's nothing wrong with that. All right, I don't think we did a screenshot of the last one. Can't remember. Let's screenshot those two. Ay, ay, ay. All right, let's screenshot those two. I'm sorry if you can hear the airplane in the background. It's really very fun. Right, and then I'm going to give you one more to try in these last 5 minutes. And then we'll end up. Right. Okay, so I want you to determine the derivative of the following. Right, so try this last one for me. There's got 5 minutes left, so I'll give you 3 minutes just because there is a root there that you need to deal with. And then we will have a look. Just a question, why can't we derive everything right away as the derivative of x is 1? Okay, hang on, let me reread this. Why can't we derive? I don't think I'm understanding your question, and I might just be having a real brain fart, but can you maybe unmute yourself, Joanne, and explain to me what you mean? Like I said, I might just be having a brain fart. I think I understand, but I also don't think I'm understanding it right. Can you hear me? I can see you unmuted, but I can't hear you. Just make sure if you've got headphones and they are connected to the sound. Sorry guys, since I can't let them just line overhead. Okay, I still can't hear you. I'm going to make an assumption of what I think you mean, and if that's not what you mean, just correct me. Okay, so as I'm understanding, when you say go straight away, because you've got that x in the denominator, you kind of just subtract an x from all of these and then find the derivative. So essentially not necessarily needing to go the step of separating your fraction and understanding rather that you would take away an x from the x squared, an x from the negative 3x, and then just bear in mind that you've got the x to the negative 1. And so as long as you understand that and go straight to a derivative, that's okay. But just remember that we are testing format here. So we would ideally like to at least see this step, that you've understood how to simplify with that denominator of x and get rid of it. But you don't necessarily need to show the split fraction. I don't know if that answers the question. Like I said, I might just be having a brain fart, but let me know if I'm on the right track. Okay. Oh, and then I muted myself. Cool. Right, let's have a look at this last one in this last minute. So issue here is obviously the fraction and the square root and all of these fun things. So we need to fix that. Now this one, I'm going to have to separate my fraction. So 5x squared over x. And this would be minus 4x to the power half over x. So the first term simplifies nice and easy. It's just 5x. But now we need to remember that when we divide with the same bases, we subtract an exponent. So this is x to the power 1. And so when we now go and simplify this, it would be x to the power half minus 1. So it'd be x to the power negative a half. So this simplifies to minus 4x to the negative a half. And now I can find my derivative. So we introduce our notation. 5 plus 2x minus 3 over 2 is our derivative. Again, if you want to put a positive exponent, go for it. But that's it. Just so that you understand where this has come from, negative a half times negative 4 is positive 2. Negative a half minus 1 is negative 1.5, so negative 3 over 2. That's why we got that. Kunena, I also pronounced your name hugely incorrectly. I'm very sorry. My brain is clearly having a brain problem.